Hello, I'm Josh Starmer. Before we get started, I want to let you know that the following presentation and question and answer session was supported by XP Incorporated. If you'd like to learn more about XP Incorporated, there's a link to their website in the description below. All right, let's get started. Hello, I'm Josh Starmer, and welcome to my presentation for XP Incorporated. Today we're going to be talking about the elements of StatQuest, or how to clearly explain complex topics. Alternatively, we could call this StatQuest, Clearly Explained. Note, this presentation does not assume you have ever heard about StatQuest before, so if it is new to you, don't sweat it. StatQuest is my YouTube channel. Every day, over 30,000 people around the world watch StatQuest to learn statistics, beep, 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 machine learning, beep, 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 and other data science subjects. But it wasn't always like this. I used to work in a genetics lab and helped people with statistics. I didn't want them to think what I was doing was magic, so I made a little PowerPoint presentation to help explain the concepts. Eventually, on February 3rd, 2015, I uploaded a little presentation to YouTube that explained R squared. My goal was simply to have it as a reference for coworkers. In other words, I didn't think anyone else in the world would watch it. However, over the next year, 123 people watched my video, which was pretty cool. And 2 people subscribed, which was super cool. And over the next few months, I uploaded a bunch of cooking videos and other StatQuest videos for friends and coworkers. So I had a video on how to cut an onion and a video on how to chop garlic. And anyway, my channel stayed small, which was fine with me. But then I uploaded this video, which attempted to demystify some of the technical jargon associated with high throughput sequencing. And if you don't know what high throughput sequencing is, don't sweat it. The important point is that in the first year, 7,000 people watched this video and 48 people subscribed. And that was 57 times more people than watched my R squared video. In other words, things in StatQuest land were going bonkers. However, to put my 7,000 views into perspective, in the same year, 2015, Taylor Swift's Bad Blood music video had something like 1 billion views. Anyways, to make a long story short, I kept adding videos to my channel, and I switched from using PowerPoint to Keynote. And now people have watched my videos over 14 million times, and over 290,000 people have subscribed. More importantly, people say that StatQuest helped them win data science competitions, pass exams, graduate from college or university, get jobs. And so far, no one has told me that StatQuest helped them get married, but maybe one day that'll happen, and that would be a cool thing too. People watch StatQuest because it makes complicated sounding things easy to understand. Here's a quote from someone. They said it's the best video one can find to understand SVC, support vector classifiers, and SVM, support vector machine algorithms. And this person said, I'm always blown away by how you make statistics and machine learning algorithms so simple to understand and how you graciously share your knowledge. This guy said that they clearly understood it. And this, someone else said that they thought I was good at explaining concepts. More people, goodness. So anyways, let's talk about the things that I do to clearly explain complicated sounding things. Rule number 1, Focus on the main ideas. This is a lesson I learned from my father. He always told me to focus on the main ideas. So imagine we wanted to teach someone how to drive a car. Should we start by teaching them about fuel injection? Or should we start by describing the master cylinder? And what about the head gasket? Who knows what that does? Even though fuel injection, master cylinders, and the head gasket, they're all critical parts of cars. They are not the main idea. In other words, we don't need to know about these parts in order to drive. In fact, even though I would bet most of the people watching this seminar know how to drive, I'd be surprised if they knew about these car parts. If I wanted to teach someone how to drive, I would focus on the main ideas. I would start by teaching them about the brake pedal so they can stop the car. Stopping the car is the most important thing to teach first so that we can avoid hurting other people and ourselves. Then I would teach about the steering wheel so that they can turn the car. We can now go left and right. We can avoid hitting things. The steering wheel is the second most important thing because we can use it to avoid hurting people. Lastly, I would teach them about the gas pedal so they can move the car. The brake and gas pedals and the steering wheel are the main ideas of driving because we need all three to drive. But you don't need anything else. Knowing about the brake and gas pedals and the steering wheel may not make someone a great driver, but at least they know how to practice and they can easily learn more once they've started. So bam, that's rule number one. Similarly, when I want to teach someone about the normal distribution, I start by describing this graph. For this specific normal curve, the x-axis represents height measurements of women in Brazil. The main idea, the first main idea of the normal distribution is that the red area under the curve represents the probability that a Brazilian woman's height will be within a range of possible values. For example, 95% of the area under the curve is between 142 and 169. And that means that 95% of the Brazilian women were between 142 and 169 centimeters tall. In other words, there's a 95% probability that each time we measure a Brazilian woman, their height will be between 142 and 169 centimeters. The main idea number two is that the average height, 155.7, is at the center of the bell-shaped curve. And main idea number three, the y-axis represents the likelihood of measuring someone with a specific height. In other words, because the curve peaks at the average height has the maximum likelihood value. Bam! Now that we understand the main ideas behind the normal curve, we can dive into the math behind it. However, I'm going to save that for later, since right now we are focusing on the main ideas. So this is rule number one, and it is the most important rule of all. It seems very simple, but it is easy to be distracted by things that are not the main ideas. And I would say the hardest part of my job is sifting through all of the information to find these nuggets that are the main ideas, because most people don't present information or when I read a book, they're not organized in terms of main ideas. You have to search for these things. Okay, that brings us to rule number 2. Have empathy for the audience. Everyone has different experiences, backgrounds, and perspectives, and it is important to keep this in mind when explaining anything. For example, if I'm going to teach someone how to drive and they know how to ride a bike, then I will explain how to drive in terms of how to ride a bike. The handlebar is the steering wheel, and the pedals are the gas, etc. In contrast, if they knew how to ride a horse, then I would explain how to drive in terms of how to ride a horse. Giddy up. And if someone had piloted a boat before, then I would explain how to drive in terms of how to pilot a boat. Anchors away. Lastly, when you don't know your audience, try your best to explain in a way that anyone could relate to. And try to anticipate questions from people that have different experiences. One way to explain things so that anyone can relate to the subject and helps anticipate questions is to use pictures. And that leads us to rule number 3, use pictures. A lot of people are visual learners. If you're not a visual learner, and it's easier to look at this than look at this, then you need to make sure you understand rule number 2, have empathy for the audience. Regardless of whether or not you are a visual learner, visual cues often make things easier to remember. Here's an example of some unvisual directions to the grocery store. 1, go straight for 731 meters. 2, turn pi divided by 2 radians. 3, go straight for 1,196 meters. 4, turn 3 times pi divided by 2 radians. 5, go straight for 52 meters. Bam! Did that get us to the grocery store? Technically, it did. Here's a pop quiz. Can anyone remember the first step in the directions to the grocery store? Go straight for 731 meters. This may be precise and accurate, but it's very hard to remember. Here's an example of a visual direction to the grocery store. Go straight till you get to the gas station. Turn left. Go straight till you get to the church. Turn right. Go straight till you get to the grocery store. Bam! To summarize this rule, we almost always have a choice between using pictures to explain, we almost always have a choice between not using pictures to explain something, and we could just step through these very precise and very accurate directions that are very hard to remember, and we can use pictures to explain something. And when we use pictures, it's a lot easier to remember because pictures are, 1, easy to relate to, often help people answer their own questions, and they're easy to remember. So bam! Rules 4 and 5. Repetition is helpful, and do the math. No matter how simple the equation, plugging in a few numbers makes it way easier to explain. And doing this more than once makes it way easier to remember. However, for complex equations, Plugging in numbers is crucial and can provide deeper and more memorable insights. For example, this is the equation for the normal curve. The mean, mu, for this specific curve is 25. So we can plug in 25 here, and the variance, sigma squared, which controls how tall and wide the curve is 4. So we plug in 4 here, and we plug in 4 here. We can now plug in different values along the x-axis for x. For example, if we plug in x equals 20, then the equation will give us the corresponding y-axis value. So let's do the math and figure out this y-axis coordinate. First, we subtract 25 from 20, and we get -5. Then we square -5 and get 25. Then we multiply by -1 and get -25, which we divide by 2 times 4, which is 8, and we get -3.125 in the exponent. E to the -3.125 is 0.04. So we end up with this term times 0.04. And the whole thing is 0.008. And that means when x equals 20, the y-axis coordinate is 0.008. Now, if we wanted to find the y-axis value for the highest part of the curve, then we would plug in x equals 25 because that is the middle of the curve. Now when we do the subtraction, we get 0. And that means this term is 0. So the whole exponent is 0. And e to the 0 is 1. So we end up with this term times 1. And that just leaves us with just this term, which equals 0.2. And that means that the highest part of the curve is 0.2. To review what we just did, we started with this big fancy equation, but when we plugged in 25 for x, the same value as the mean, the exponent ends up being 0, and we ended up with this term times 1, and that left us with just this term to determine the y-axis coordinate for the peak of the curve. Note, if we had another curve with another mean value, so in this case mu equals 15, and we wanted to know the y-axis coordinate for the peak of the curve, then we could plug in x equals 15 here, and that makes this term 0, and the whole exponent becomes 0. So this term equals 1. And that means all we really need to do to determine the maximum y-axis value on this curve, or any normal curve, is just calculate this part. In this case, the variance equals 2. So we plug in 2, then we just do the math, and the maximum y-axis value is 0.28. Now we have seen 2 examples where, when we want to know the y-axis coordinate for the peak of the curve, we can ignore this part of the equation. And that means we don't have to plug in values for x or for the mean, mu, because the whole term cancels out. And all we have to do is calculate this part. Bam! Now, if we want to find the y-axis coordinate for the highest point on this curve, we don't need to know the mean, mu, or some value for x. Instead, all we need is the variance, sigma squared. In this case, the variance is 16. So we plug in 16, do the math, and we get 0.1. So 0.1 is the maximum y-axis coordinate for this curve. Double bam! Okay, now remember the rules we just illustrated here. Repetition is helpful, and do the math. We just did both of those. And we just went through plugging numbers into this equation a few times, and we learned that we can omit this part when we just want to know the y-axis value for the peak. All right, rule number 6. Don't repeat other people's explanations. This might be personal for me because my job is to explain things to people. But my rule is if someone else already has a great explanation for something, what I do is I direct people to it. I don't feel like I need to re-explain it. If I can't do any better than that, then I'm just going to say, hey, if you want to understand this concept, check out this other website, check out this other video. Don't come to me, because that other person has done the best job out there. Otherwise, if there is no other good explanation, you have no choice but to come up with something new. Now, in YouTube land and on the internet, there's sort of this echo chamber effect. And once somebody explains something, regardless of how good or bad that explanation is, a lot of people just copy it. Word for word, or generally speaking, they might use the same data set as an example. They might use the same terminology and the same graphs. But that's not very helpful, because if someone goes to some website or a YouTube video and they watch something or they read something and it doesn't make sense to them, well, if someone else just repeated that same stuff, that's not going to help that person. They're going to go to the next link down in the Google search, and they're going to find the exact same explanation, maybe with a slight change in words, but there won't be a big difference in how it's explained. And that means that if that person didn't understand the first explanation, they won't understand the next explanation. And they won't understand any of those explanations unless someone comes up with something new, with a new way to explain something. And that leads us to rule number 17. Limit the presentation to 3 main ideas. And I know this is kind of like a little funny because I'm on rule number 7. So I've already violated my own rule. But when I'm making videos, if you've ever watched a StatQuest, you'll notice that I do 3 BAMs. I have a main idea and I go, hey, bam, that's great. And then we go on for a little bit longer and I get really excited because we're covering really cool material. And then I say, hey, double bam. And then we go just a little bit longer and then we finally reach the climax, and that's the triple bam. And the reason why I use 3 BAMs is to accentuate the fact that there are 3 main ideas that I'm covering. I've found that when I'm making a video and I want to add extra BAMs, I've gone too far. I've swerved and deviated from the point of the video, and I'm covering subjects that I don't need to talk about or would be better separated in a different lesson. And I found that just in general, if you can keep whatever it is you're trying to explain as simple as 3 main points, then your explanation will be easier for people to understand it. Okay, I do have some other random thoughts that may be helpful when presenting stuff. One, I know this sounds crazy, but try not to use a laser pointer. You'll notice that right now, I'm not using a laser pointer. Um, I don't have an option to use a laser pointer. On YouTube, you can't use a laser pointer, I guess. Um, so I have no choice but to use sort of still images. Uh, and I've got strong feelings. It's funny when I first started doing StatQuest videos and I switched to doing things on YouTube, I was very scared that I didn't have a laser pointer because I was like, well, how am I going to point to things that are important? And I've just since discovered that not only can you make a presentation without a laser pointer and give a presentation without a laser pointer is actually a crutch that can get in your way. And let me explain why. I have two kittens. The one on the left is named Red, and the one on the right is named Poe. Those aren't the main ideas, but I just thought you might want to know. They love it when I point at things with a laser pointer. But they are not paying attention to what I'm pointing at. Instead, they are obsessed with the green dot itself. They love it because they have an instinct to track motion. And so wherever I point that green laser pointer dot, my cats will chase all over the house to try to get at that dot. They don't really care that one time I'm pointing it at the pillow and then I'm pointing it at the rug. They could care less about the rug or the pillow. What they're interested in is the green dot. People are not kittens, but we are not that much different. Because it's moving around, we tend to see the dot instead of what it's pointing to. So instead, focus people's attention by putting a box around it and pointing to it with a stationary arrow. Now we can all focus on this specific part of the equation that we're interested in talking about. And try to remove everything that's not directly related to what you're focusing on. So now, when we look at this part of the equation, we can meditate on it without any distractions. And that's very important to make sure you've got people's concentration focused on what you want them to be focused on, and not just a green dot that's been moving around on the screen. Okay, my second advice is dare to look stupid. If I went up to the average person on the street and I said, let me teach you about this equation, there's a great chance that they would run away screaming, no, that looks complicated. I can't do that stuff. And that would make me look smart, but I would not have explained anything to anyone. In contrast, if I say, let me explain this curve to you, there's a chance they will say, hey, that's too simple. You must not be very smart. And they could ridicule me. That's okay. That's a risk I'm willing to take. And I hope you're willing to take it too, because if we start simple and build up, then I know I haven't lost you. If we start with a real simple example and we build on it very slow and very in a concerted way, in a directed way, I know you're following what I'm talking about. But if I start with something very complicated at the very beginning, there's a good chance I've already lost you, and adding things to that complicated equation or whatever it is that was complicated will not help. So I like to start simple, and at the risk of looking silly and looking not smart, we're going to build from there, and we're going to get to complicated soon enough. Yeah, excuse me. In summary, I believe that StatQuest, my YouTube channel, is successful because rule number one, we like to focus on the main ideas. Rule number two, we have empathy for the audience. And that means trying to understand where they're coming from, what their experiences are. Do they know about data science? Do they know about the normal distribution in advance? Or do they not know about it? Do you have to start from scratch? You have to know about your audience in order to know where you can start the conversation. And if you don't know your audience, start simple and build up. Rule number 3, use pictures. I know I'm not using a picture right here, but you get the idea. Remember, if we're trying to tell someone directions, we don't just list a bunch of directions arbitrarily. If we give them pictures, or we even just describe things in terms of pictures. If I say, hey, just go down the street until you see the snack shop and turn left there, someone has an image in their head. They're thinking, oh, I'll just look for the snack shop and then I'll take a left. In contrast, if I say, go down the road 553 meters, who knows what they're going to do? They may go down far enough, they may not. It's hard to measure that when you're just walking and you're not really concentrating on the exact distance of every step. Rules 4 and 5, repetition is helpful, and do the math. If there's one thing I think that sets my channel apart from a lot of the other channels, is that I do the math and I do it repeatedly. And it helps people. People go, oh, I see how you're just going through it and you're plugging the numbers in. I can do that myself, and I can take this lesson and I can plug in my own numbers now. Now that I've seen how StatQuest does it, how Josh does it, I can plug in my own numbers and see what I get. Do I get the same results? People do that all the time, and the funny thing is they often find that I'm not very good at doing the math technically, and I have a lot of errors. But the main idea is just plug in some numbers and you'll get something out. Rule number 6, don't repeat other people's explanations. If they have a great explanation, then just say, hey, check out this explanation. It explains the normal distribution better than anyone else in the world. But if it's not the best explanation, you looked at StatQuest, you looked at some other websites, and you were like, I don't think this is the best. Well, then you have to come up with your own, and you can't just repeat what other people are saying. And rule number 7, which we violated all over the place, limit the presentation to 3 main ideas. All right, that's the end of the talk. I know we've got a bunch of questions. We've got plenty of time for those. Is it okay if I exit? We've got a bunch of questions over here. Let me just reload my window. Okay, so someone said, I'm just gonna read through these questions and give you the answers, or my answers. There's no right answer or wrong answer. So someone said, you're the most didactic guy on the internet. What recommendations would you give data scientists to communicate with non-technical coworkers inside of a company? Well, I guess that presentation that I just gave you answered this question. 1, focus on the main ideas. 2, I can't actually remember the next one. Is it use pictures? And 3, repeat, use and plug in numbers, and have empathy for the audience. That's the one I must have skipped that one. It's kind of funny. I'm not a good example of my own teaching technique. But anyways, if you have empathy for your audience and you know they're non-technical, try to keep it non-technical. Don't just throw around a lot of fancy jargon like, this is the posterior distribution of the beta binomial hypothesis test. They're not going to understand a word of that. However, if you can give them a general sense of what the main idea is, the jargon is never the main idea. The main ideas are always the concepts. So focus on the concepts of what that posterior probability of that beta binomial distribution is. What's the main idea behind that? Not the jargon, not the words, but the concept. So that's question number 1. Question number 2, any thought on the future of big data, machine learning, and applied statistics as a profession? How can one study and prepare himself or herself? Well, my thoughts are that big data is just going to get bigger and more of it. People are measuring everything, and our ability to amass data is not going to go away. There's not going to be something that like completely breaks the internet. Um, we're just going to keep collecting more and more data, and it's going to be finer. You know, it used to be, 10 years ago, if you had a client and you knew basic demographics like their age, then you were doing pretty good. Nowadays, we've got so much data about all of our clients. We might know their age. We might know it down to the day of the month. We might know what their shopping preferences are, what websites they like to go to, how much time they spend on the internet. It sounds kind of creepy and big brothery, but this is the reality we live in. We live in a connected world. Um, so it's and people are going to be measuring these things. And so we're just going to collect more and more data. I used to work in a genetics lab, and when I started working in the genetics lab, we'd be lucky if we could measure one or two genes at a time. And then all of a sudden we could measure all of them, all 20,000 human genes at a single go. And so we went from having, being data poor to being very data rich. And now what they're doing is instead of, it used to be that they'd have to average the 20,000 genes over a large group of cells. So if we were interested in a tumor, for example, or a cancer, we would apply this research technique to a big blob of that tumor, and it would give us the average gene activity for all of the genes in that tumor. But now we can do it on a single cell basis, and everything is made of millions of cells. And so in biology, the data is just exploding. Okay, so you don't need me to talk more about what the future of ML is, because we're just going to have more and more data, and machine learning and applied statistics are just going to become more and more critical every single day. So the last part is, how can we study and prepare for this profession? Well, there's StatQuest, there's the internet. You can watch my videos, of course. But there's just lots of things you can do. My favorite book on machine learning is a free download. It's called The Introduction to Statistical Learning in R. It's written by a bunch of super geniuses, and I love it. I'm going to be honest with you. It's kind of hard to read. It's not the easiest reading ever. It doesn't have a lot of pictures on every page. However, it does have one thing going for it, in that I've made a lot of StatQuest videos to correspond to the chapters in that book. So what you can do is you can read that book or skim through that book or do whatever you can with that book. And when you get confused, you can say, hey, I wonder if there's a StatQuest video. And you can, oftentimes there is. So if you want to learn about regularization and you're reading in the book about regularization, you're like, it's kind of confusing. Well, you can check out the video, and it's there and it's waiting for you when you need it. There's also a bunch of websites that I love. The UCLA, they have an online statistics consulting website. And I think, I'm not really certain, but I assume that if you are an employee at UCLA and you need statistics, you contact those people. But this website is actually for everybody. They have great explanations of like what logistic regression is, or all these data science and statistical learning techniques, and they've got great examples, and they've got it in all these different computer languages. So you could learn how to do it in R, you could learn how to do it in SAS, you could learn how to do it in SPSS. So whatever sort of, however, maybe in Microsoft Excel, whatever you use to do data science, they usually have an example of how to do it in that language. I just love the way they write up stuff. It's very intuitive for me, and it's a place that I go to when I'm researching my own videos. Another place I really love is, there's a university in Pennsylvania. It's not the University of Pennsylvania. It's Penn State, or Pennsylvania State. They have a wonderful online statistics resource, and I love reading through those pages. Okay, so that's the answer to that question. What is my opinion about AutoML tools, both for model and feature engineering? So if for those of you who are not familiar, AutoML is like, so in machine learning land, we have a lot of different ways to apply machine learning to the same data set. There's all these fancy algorithms like neural networks or cat boost or XGBoost or support vector machines. There are all these fancy machine learning methods, and we can apply them all to our data. What AutoML does is it applies all of them simultaneously to the data, and it tries to optimize them. So one thing about machine learning is every single method, neural networks, XGBoost, support vector machines, they all have these things called hyperparameters, which are really fancy terminology for fudge factors. All of those things have little parameters that we can tweak, and if we change one value sort of arbitrarily, it can change how good or bad our machine learning algorithm is. And AutoML attempts to, one, apply a bunch of different statistics and machine learning methods to our data, and two, it tries to optimize them. And also, it can also be used for something called feature engineering, which is sort of like selecting what are the most important features in your data set that you should be focusing on. Oftentimes we collect a lot of data. Some of it's useful, some of it's not useful. And feature engineering is a lot about that process of filtering out the parts of the data that are not very useful and sort of streamlining it to just the good stuff. So AutoML is a relatively new thing on the scene, and I on the one hand, it sounds awesome, right? Because there's all these different methods. Getting them all optimized and measuring them all is a terrible thing to have to do. That's a lot of work. It's not very fun to do. So that's very cool. Although I will say you have to be careful with how you do it. You know, if we throw like 100 different methods at our data, there's a good chance that by random chance, one of those is going to do really well and perform really well. Does that mean that that same method is going to work well in the long term? In other words, it just so happened that this one method worked really well because it just overfit the data in just the right way. That if once we give it new data, it can no longer perform really well. It does great in the testing situation, in the testing environment, but not in the. So there has to be some way for compensating for the fact that we're looking at all these different models. And just by chance, we might have one that maybe is giving us good results just because of the data set we have and not because of its good in the long term. So when you do AutoML, you should look and make sure that you're aware of those features. I should stop sharing so you can see my lovely face. So what else do we have? Someone said, in my opinion, what is the future of data science 10 to 20 years from now? What will be the skills required? This is kind of an interesting question. I think I'll tell you immediately off the top of my head, whatever it is, we won't call it data science. So when I went to graduate school, I have a PhD in something called bioinformatics. When I went to school, they just invented that term. Bioinformatics was a new term. No one had ever heard it before, but there was a program at NC State University, North Carolina State University, for bioinformatics. And to be honest, I'd never heard of it either. In fact, I didn't even apply to this program. I'd applied to something else. But the people that saw my application said, this guy would be great for bioinformatics. Let's pass his application over to those people and see what they think. And the bioinformatics people contacted me and said, hey, we got your application. We think you'd be perfect. Why don't you come interview? So I went and interviewed. And I asked the head of the bioinformatics department, I said, hey, what is bioinformatics? And the head of the department, this guy named Bruce Weir, said, bioinformatics is a hat we put on. And when we put on this hat, we're eligible for certain funding that we were not eligible for before when we called ourselves statisticians. And the lesson there is that Bruce Weir was a statistician before he called himself a bioinformatician. And after he called himself a bioinformatician, he was still a statistician. The skills we learn in machine learning and data science, these things are going to be useful for all of eternity. For example, not all of it. I mean, that might be an exaggeration, but think about the t-test. The t-test is one of the most basic statistical tests. It's been around forever, or at least 100 years. Linear regression is still a very popular and very useful machine learning method. It's been around for almost as long. Knowing about these core concepts, these core ideas, will be good for 10, 20, 100 years from now. Will they call it data science? No. They're going to call it something else. They'll call it data awesomeness or crazy statistics. Who knows what they'll call it? But I just know from experience that they will change the name. And that at some point in your career, you're going to have to say, I'm no longer a data scientist. I'm now a data, super genius, or whatever the new field name is. And that's just part of life. We love fashion in clothing and food and things like that. We love having new things. And unfortunately, our career is just the same. Things come and go in terms of the terminology and the way we phrase things. That's all fashionable as well, and it changes. However, the core concepts of how to do data analysis, those don't change. Those have stuck with us for over 100 years. So that's my prediction of the future. The name's going to change, but what we do is going to be the same. And sure, there's going to be some cool new algorithms we're going to learn. We're not going to stop learning new cool stuff. But the tools we're developing now, I don't think they're going to go out of fashion in themselves. We might have to call them different things, but we'll still be using the same tools. Someone said, I know you've worked in academia, and that's true. What are your thoughts on the use of statistics and machine learning in academics versus industry? What can they learn from each other? So academics and industry have two often very different goals when it comes to data. So an academic's perspective is almost always a research perspective. They have a big pile of data, and they want to know what that data can tell them about whatever they're trying to research. For example, I might have a lot of data about buying habits and or purchasing habits, online purchasing habits, or online stock trading habits, or something like that. I might have a lot of data about that stuff. But as an academic, I'm not necessarily interested in classifying people as someone who's going to buy a lot of stuff on the internet versus someone who's not going to buy a lot of stuff on the internet. What I'm interested is in understanding those people, those different types of people. What makes people that buy a lot of stuff on the internet, what makes them what they are? And what makes people who don't buy a lot of stuff on the internet or buy a lot of online stocks, what makes them sort of who they are? What do they do? What are their habits? How can I understand the people underneath the label? And that's what an academic researcher is often understanding. They often interested in understanding. They want to know sort of not just the labels of the categories of the people, but what's underneath it. Whereas in the industry, we're often just interested in those labels. Is this person going to buy something from our website or not? Are they going to buy stocks online or not? If I'm driving a car and that car is automatically driving itself, the car's perspective is there something I'm going to hit in front of me or not? Whereas a researcher, an academic researcher might go, we have all this data that suggests we might run into something. I'm interested in what that means. What is it? Can I sort of quantify that thing and try to understand it? Whereas in industry, they just want to label as something I'm going to hit or not, and needs to be avoided or not in the self-driving car. So academics and industry often have fundamentally different approaches to data. So the question is, I think they can learn from each other? And the answer is yes. Because I think, academics sometimes, traditionally, they just get lost in the details. Or at least that's the stereotype. We make fun of academics as people that are lost in the forest, and they just don't know what's going on. Their heads, there's so many details that they can't make a decision. On the other extreme is the sort of the industrial perspective, is where all they want to do is make a decision. Is it black or is it white? I need to know one or the other, and I just have to do something. And I feel like both of them could learn from each other, in that understanding the underneath the labels, that could be useful for making long-term business decisions, not just immediate business decisions. Sure, a car has to avoid something if it's automatically driving by itself, but it'd be also useful to understand in the long term, what was that thing that came out in the road? Is there a way I can anticipate it? If I learn more about it, can I avoid it in the future without even having to make this decision of, am I going to hit this thing or not? So I think both fields can learn from each other. What else do we have? Okay, someone said, recently, Jeff Bezos banned PowerPoint in meetings. How could we start discussing data science of this kind of subject without presentations? Is that possible? So this is really funny, actually. At the very beginning of the pandemic lockdown, I had a friend who teaches English at a high school. So these are 14 to 17 or 18-year-old children. He teaches English, and he sent me at the very beginning of the lockdown. He was asking me, because he has to start teaching online, and he was asking me for advice on how to teach online. And he sent me this pamphlet about how PowerPoint should be abolished, and how we should just have these memos, well-written memos, like 1 or 2 page long memos that we should refer to instead. And it's funny because I was on the BBC yesterday, and I was watching this video about Jeff Bezos, and it was like, yeah, he doesn't use PowerPoint. He makes people read these memos. And I was like, man, he must have read the same pamphlet that I read. So it's a very fundamental thing. So I'm going to just go out and just say this. I would say 99 people out of 100 misuse PowerPoint. I don't want to brag, but I feel like I know what I'm doing because I've got good results. I've actually got data suggesting that when I use PowerPoint, I use the equivalent of PowerPoint. I use something called Keynote, which is Apple's version of PowerPoint. But when I use PowerPoint, I know I'm effectively communicating to people because they write me back and say, I just passed my exam because of what you did. They write me back and say, I just got a job because of what I saw on the internet that you did. So I know I can effectively communicate with PowerPoint, and I can effectively convey images or concepts. But I also know that most people cannot. Most people, they don't follow the rules of focusing people's attention on the screen. They have a laser pointer and they're pointing all over the place, and your eyes are looking all over for that laser pointer and you have no idea what they're talking about. People put a full screen full of data and it's completely overwhelming. And instead of listening to what the person says, you're just looking at the data, just like completely like in some weird brain dead zombie state. People misuse it all the time. So the question is, what do we do about that? And one, we can learn how to use PowerPoint better. I mean, obviously, you can go to the extreme of abolishing PowerPoint, and that will train you to do certain things. I'm actually doing that myself. I'm now creating StatQuest study guides, which are PDF documents that are where I take all of the knowledge of a single StatQuest video and I put it into a 5 or 6 page memo. And this is a great exercise for me because one, it makes you focus on the main ideas because you've only got, I don't want this to be 1,000 pages. I want this to be a short, crisp, easy to consume memo. So it forces you to focus on the main ideas. And so working on a memo is a great thing. PowerPoint makes it too easy to add additional slides and just say, hey, we're going to talk about all this stuff. No, if you keep it to 3 points, 3 main concepts, you'll do much better. So if you can tell, you've asked a question about something I'm very passionate about. One, we can learn how to be better at PowerPoint. That's a huge, huge thing. And I think if we were better at PowerPoint, the whole world would be great. But I don't think it's necessary to entirely ban PowerPoint. I feel like you can still convey concepts without it. However, with PowerPoint. However, I also believe you can do it without it. I even believe you can convey complicated machine learning concepts, and I'm trying it myself with the study guides that I'm creating. So the next question is, they said they've never seen a StatQuest on neural networks or deep learning, and they say, do I think they're overrated? So I am working as hard as I can on neural networks StatQuest because there's a lot of demand for it, and it's something I want to understand as well. So I've got my own incentive to try to understand these concepts. And I'm working on these videos right now. The first one is going to be out for early access on Monday, and I hope the next one is out by the end of the month. But what do I actually think about these? I'll be honest. I lived in an academic setting for a very long time. And to me, what's really interesting about data isn't just yes, no, black, white, making decisions. I'm also interested in understanding what's going on underneath those decisions. What is the data telling us about those people? And can that data help us generalize to the greater world and things like that? So as an academic or a former academic, I like machine learning methods that can easily generalize to teaching me about the people underneath underneath the call of yes, no. And neural networks, they're terrible for that. And so I've never really had a good use of neural networks on my own because I've always used methods that allow me to look under the hood and learn more about the data. And neural networks are just terrible for that. So are support vector machines. They can do a good job of telling us yes and no, but they don't really tell us anything but those things. And so for those reasons, I've kind of been a little turned off about those methods. However, the question is, do I think they're overrated? And they obviously are very hyped. I think what's really important is I think it's important for people to understand what they do and how they do it so that they can understand what neural networks are good at and what their limitations are. I think, I guess now that I'm talking about it, I would say that neural networks probably are overhyped and overrated because people do not fully understand their limitations, and they are very limited. Um, and that's one of the big motivations I have in making the videos that I'm working on right now is sort of to illustrate so that people all over the world can understand what neural networks are, what they're good at, and maybe what they're bad at. What are their limitations? We need to understand those things. And I think a lot of people in Silicon Valley and sort of in business think that they're limitless, and they aren't limitless. They run into limitations all the time. Okay, next question. How did I come up with the concept of silly songs and saying "bam"? Um, for me, uh, I'm a relatively silly guy. I've dressed up in a nice shirt, but that's just because I'm doing a talk for business people. But I'm very much a laid back guy, and I just like being silly. That's just part of who I am. I'm just a silly guy, and I like silly humor. And so when I record a StatQuest, making a StatQuest can take months, and I do the research, I make the slides, and then I finally record the voice and I put everything together. And I've spent months on it. And the way I celebrate is the very last thing I do is I sing a silly song, and it's completely improvised. I don't practice it. I don't write it. And you can tell because these are really bad songs, but they're super fun. And it's just stream of consciousness. I pick up an instrument, and the first thing that comes to mind is what that song's going to be. And it's just my way of celebrating the end of this long couple of months process. And it's funny because it's the first thing you see, but it's really me celebrating the completion. It's me having a little party, a little one-person party saying, hooray, I finished doing all this work and I'm going to celebrate. So that's where the silly songs came from. Where did BAM come from? I have no idea. There used to be a famous chef in the United States called Emeril Lagasse, and he said BAM all the time. But is that why I say BAM all the time? I don't know. I do know that I was saying BAM a lot when I was doing these, when I was talking, when I worked in my old job, I'd be talking to my lab members and I'd say BAM. And I remember I wanted to add more emphasis to a point. And I was like, what do I do if I've already said BAM? And I thought, oh, I'll say double BAM. And double BAM is going to be twice the emphasis. And so that's where double BAM came from. And naturally, when you've got double BAM, you got to take it one step further, and that's triple BAM. And that's just craziness. So that's where all that stuff came from. Someone asked what my favorite machine learning technique is and why. I love tree-based methods, and I love them because, one, they can be very good, like XGBoost can be a good classifier. But I also love them because they let you look underneath the hood and see what they're doing and learn from your data. So it's sort of like the academic's dream come true. It lets you investigate the data and learn about what's going on in a big picture, but it also gives you relatively good decision making, sort of yes no decisions. What else we got? Could I improvise a final silly song for XP Incorporated? It is possible. Let's save that one for the end, because that's the way I want to end this one, I guess. Okay, someone asked. They said, "You're a full-time YouTuber, and why and when did you decide to make a living off YouTube? If not, are you considering it?" So that's a. I am a full-time YouTuber. This is what I do for a living. I don't do it for the money because I'm barely making enough to get by. However, I made a decision because I was in academics, and in academics, you're supposed to write publications and manuscripts and sort of publish in journals. And writing a publication is about a 2-year process. For me, it was. You do your research, you write it up, you try to get it published in a journal, they reject it, they give you all these reasons why, you have to go back and do more research, blah, blah, blah. And eventually, after 2 years, it gets published. Now, I'm not a famous academic, never was. And so when I publish, maybe 100 people are going to read that thing, and this is 2 years of effort. Maybe 100 people are going to use that, read it, maybe, and then maybe one or two, if I'm lucky, it'll change or affect what they're doing in their own research. In contrast, with StatQuest, I can make a video, and within a day, 5,000 people have watched it, and it's helped people all over the world. And it was about 5 months ago or 6 months ago, I was sitting there at my desk, and I was thinking, what's the most important thing I could be doing with my time right now? I could be doing a lot of things. I could be sitting on the beach doing nothing, but that would not be the most important thing I could do with my time. I could go hiking in the mountains for the rest of my life, sit on a hill and never talk to anybody. I could possibly do those things, but that would not be the most important thing for me to be doing with my time. And I was saying, well, I could work on this publication, or I could work on my videos. And it just dawned on me that working on my videos is the most important thing I can do with my time. And when I made that decision, I left my job 2 weeks later, because I firmly believe that making these videos, explaining these concepts, going deep into statistics and machine learning, I believe that's me spending my time on the most important thing I can do. So that's why I did it. It was very scary. It was like jumping off a cliff, and I panicked for a while, because for the first month, I took a huge pay cut. I was a professor at a university, and I took a huge pay cut, and it was very scary. But I'm convinced it is the most important thing I can be doing with my time, and so it was worth jumping off that cliff. And I'm very, very happy I've done it. We have a lot of more questions. Actually, we only have a few more questions. So we're just going to go through them all. In theory, we were going to end at 3. It's 3:05. We're just going to go for another 5-10 minutes, if that's okay with you guys. Someone said, I've got 2 questions about the 5% rule for p-values and hypothesis tests. And people have a question like, what is my opinion about that? And this is kind of funny. So when I worked, I have a degree basically in statistics, a PhD basically in statistics. And when you learn about statistics in an academic setting, they have all these rules and things you're supposed to follow. But I've actually found that in practice, and I'm probably going to get chewed out on the internet for saying this, but that 5% really is just a guideline. It's a guideline that we use because in practice it has worked well. So whenever threshold we choose, there's a trade-off between gathering more data and how expensive it is to gather that more data. Because if you ever do like a power analysis, you'll know that the more data you get, the more power you have. And generally speaking, the more power you have, the chance that you're going to have a small p-value or a significant p-value, or a p-value under 5, if that hypothesis is correct, goes up, and it scales with the data. And so that means if we have this threshold and we want to cross that threshold, we have to have a lot of data. But gathering data is expensive. And so this 5% threshold, I think, has worked well in history as a way of balancing expense versus reliability and making mistakes. Because making mistakes have expenses as well, right? If we use a 5% threshold and we make the wrong decision based on that, well, that's going to cost us some money as well. But generally speaking, 5% has been a good balance of those things. And we know that, or I know that, because I used to be in genetics, and genetics research has not collapsed on itself. By and large, the techniques Um, and the statistics that we use in those techniques have built up in a way that builds on itself. If it was all built on a bunch of false positives or false negatives, then we wouldn't be making progress. And I believe that at least in genetics, we're making progress. That being said, sometimes we don't make the 5% threshold. And what do? What's my opinion? Often there are different ways to approach a problem. And I often say, even when we have a p-value that's small, that's less than that 5% threshold, try to find another way to test the same thing. And I like it if that test is orthogonal and it's completely different from the original test. But the idea is, if we're really going to make a good decision, we can't just make a decision, or hopefully we won't make a decision just based on one little thing. Hopefully we'll make a decision based on a lot of things. And this is the way like criminal justice is done. At least in the United States, or at least for now in the United States, the way we do it is that that person who is accused of doing some crime is innocent until we've got a significant amount of data, so much data that beyond a reasonable doubt, we believe that that person committed that crime. And it's usually not just one thing that convinces us of that. We have like DNA forensics and things like that. That's a contributing factor, but it's also like they found the weapon, or they found the motive, or they found other people that said, I saw that person at that place at that time. We have all that information, and it's not just the one thing that convinces us that that person is guilty beyond reasonable doubt. And I feel like that's the way it is with statistics. We may not have a statistical test that gives us the best p-value ever, but if we have other information that we can bring in and consider, then that may push us into that beyond all reasonable doubt region. And when we're there, we can make our decision. So I feel like the 5%, 0.05 or 5% threshold is a flexible thing. And you just have to take it in the context of all of the data and all of the stuff that goes into making the decision. Someone said, I should visit Brazil. I would love to visit Brazil. I've been twice. I know un pouco de português, and I loved it. I loved everything about it. But I've never been to Sao Paulo, and I really, really, really want to go to Sao Paulo. So I hope one day when this pandemic is gone, I will go to Sao Paulo and I'll be able to visit everybody. What else do we have? Oh, a silly song. Hold on. All right, so we're going to end this seminar with a silly song. So we're going to say XP Incorporated. Thank you for having me give my talk and answer a bunch of questions. StatQuest. All right. Thank you very much. And I hope you've enjoyed the talk, and I hope I answered your question. And until next time, quest on.